Hello and welcome to another discussion on classical motion of a single particle. So, in this sub lecture we will discuss the basic motivation of classical mechanics. So, if you remember, we said that in classical mechanics the kinematics is to describe the motion, to know where the particle is or whether at that time instant the particle is trying to move at all or not. But dynamics says that how this nature actually has been generated, or I mean what is the source of the motion or the explanation of the motion. So, now if we have thanks to Newton's law the equation of dynamics, then from that the main objective of classical mechanics is to know the position and the velocity for a constant for a particle with constant mass, of course, at any given time. And we said in a previous lecture that this is only possible when we have the total set of equations of dynamics with appropriate initial conditions. So, the condition or the deal is that you give me the equations of motion and you also give me the position and the velocity at any point of time, then I will exactly predict you at a later instant of time, okay, or at some arbitrary instant. It can be later, it can be actually previous if it is meaningful, of course. It depends how you define your instant, time instants. So, it can actually, so by the help of the equations of dynamics and the initial conditions, I can exactly tell you the position and the velocity of the particle at an arbitrary time, okay, which was not known in general, the position and the velocity. Okay. So, that is the main motivation and the main objective. So, whatever be the process of solution, if I have the Newton's law of motion, Newton's laws of motion or the equations of dynamics, if somehow by using any correct method, if I can just tell what is the x of t and x dot of t, actually my purpose is served. That is the classical mechanics main goal. So, of course, I can tell you that in one dimension, of course, in 2 dimension or in 3 dimension, this is the purpose is to know r as a function of t and r dot as a function of t, starting from d2r dt2 or r double dot is equal to f by m, okay, where f is the force. Now, in this discussion I will actually try to show you that the integrals of motion or the special constants of motion sometimes are very helpful in solving those equations in classical mechanics, and that is actually very evident and very direct in case of one dimensional motion, and I will also discuss about that. Okay. So, I am taking the very condition or the very case of a one dimensional simple harmonic oscillator. That means, you have m d2x dt2 and the force is minus kx. If the force is minus kx, then you all know that what is the corresponding potential. The potential is, so this is totally can be written as a this is a force, and if that force is equal to minus du dx, then that u should be half kx square. Okay. And so, of course, you know in this case the total mechanical energy is nothing but half m x dot square plus half kx square is constant. Now, before using this constants, before using the conservation of this total energy E, I will first tell you that the conventional method. Let us say what is the equation of dynamics for a simple harmonic oscillator in 1D, this is simply this one, and then you can easily write d2x dt2 is equal to minus k by m x. Then you know this is d2x dt2 plus omega square x is equal to 0, where omega square is equal to k by m. Now, you can now have a second order ordinary differential equation, and you know the trial solution. From our knowledge, we know that if x is equal to some a, I think I just write like this, a sin omega t plus b cos omega t, I mean you can do the other way as well, then this solution should be satisfying this equation. Okay. And why is this? Because you know, like if I do dx dt from my knowledge, that will be of course a omega cos omega t minus b omega sin omega t, and d2x dt2 will be equal to minus a omega square sin omega t minus b omega square cos omega t. Then of course, minus omega square common, you have a sin omega t plus b cos omega t, and this is nothing but your x. So, you know that this solution actually satisfies this equation d2x dt2 is equal to minus omega square x. Okay. Now, the point is that if we want to do it, I mean want to solve it more directly, then the conservation of energy, total mechanical energy actually helps us. We can do this in this way. I already said that m x double dot is equal to minus k x can be written as m x dot x double dot is equal to k x x dot. I can write this thing, as you already know, I have done this trick also for the conservation of total energy. This is nothing but d dt of half m x dot square plus half k x dot half k x square is equal to 0. And then I simply say that my m by 2 x dot square plus half k x square is equal to a constant, and that constant I now call it as E. Okay. So, this E, for example, let us say, I mean in a motion, this E should not change. Okay. If I have this force only and there is no other force is acting, then this should not change. Okay. So, then I can easily write from this step, I can easily write that x dot is equal to root 2 e over m minus omega square x square, where omega square, as I just said previously as well, is equal to k by m. Just from this equation you can easily write this equation. Okay. Now, what is this? This is dx dt is equal to root 2 e by m minus omega square x square. Okay. Now, I can say, okay, I can just take everything including this x part on one side and the dt on the other side. Okay. Dt. I also multiply with this constant omega both sides, and then I say d of omega x by root 2 e by m minus omega x whole square is equal to d of omega t. Okay. I can actually integrate now, and so you see this is nothing but an integration of the form dz over root a square minus z square, where a is nothing but root 2e by m. Okay, this e I can just write like this. Okay, and if you want to calculate that, I am also trying to calculate that. So, the easiest way, you just do some substitution. Z is equal to, let us say, a sin theta, and so dz will be equal to a cos theta. So, integration dz will be a cos theta d theta, sorry, it will be a cos theta d theta, I am sorry, root a square minus a square sin square theta. If you do this integration, so it will be actually again a square minus a square cos square theta, I mean a square minus a square sin square theta, which is a square cos square theta, under root it will be a cos theta. So, a cos theta and a cos theta will go away, you will have integration theta, which is theta plus c. Now, that theta is nothing but sine inverse or arc sine z by e. Okay. So, plus some constant. I can do the same thing over here, and I can actually again go to the green. Yeah, I can actually calculate that and clearly write this is nothing but sine inverse omega x by root 2e by m is equal to some omega t plus phi. Phi is an arbitrary constant of integration. Okay. And finally, I can actually write this omega x, okay, by root 2e by m is equal to sine omega t plus phi. Okay. And then finally, you can write x is equal to root 2e by m omega square sine omega t plus phi. Okay. You see here you can find another solution which is exactly of this same thing. Okay. But now maybe you cannot easily understand the form, because if I now tell you that okay, this a sin omega t plus b cos omega t is equal to some c I think like sin omega t plus phi, where a I can define as some c times cos phi and b I can define some c times sin phi, then it will be, so of course, so c is nothing but root over a square plus b square, and phi is nothing but tan inverse b by a. Okay. So, if you choose a and b in such a way, then you can actually find c and phi, and you can write this expression as this one. So, you see this c is nothing but this constant. Now, we root over 2e by m omega square, and you see this is the correct constant from the point of view of dimension as well, because E has a dimension of m x dot square and has a dimension of k x square. Okay. And also we are saying that omega square is having a dimension of k by m. So, if I now say that this I can actually say like this, that if I write completely, you will see that E is actually dimension of m omega square x square, because you see that this m omega square is nothing but k. So, kx square can be written as E of m omega square x square. So, 2E by m omega square will have the dimension of x square, and root over of that will be the dimension of a length. This has dimensionless. So, this is also correct. So, you see in the first method you do not know what C is, that will be given by of course the initial conditions, but here actually you know what this is 2E by m omega square, but the point is that which one is more advantageous. Actually both are equally advantageous, because this E is also given by the initial condition, because whenever I give you the initial x and x dot or the x and x dot of any instant, actually you know that this value at that instant, and since that instant is since that constant is a constant of motion, this quantity is a constant of motion, basically you can determine this one given an initial condition, and this constant then you use throughout. Okay. So, in this way you can see that you can just using the invariance or the conservation of the total mechanical energy, you can exactly solve one dimensional motions. I can actually give you some problems on on some other type of one dimensional motion, where the motion is not simply like harmonic oscillator type. Okay. For that you can actually also find out how you can solve for x and x dot to find the solution. Of course, after having found x as a function of t, now you can take x dot and to find the kinematics, the complete description of the kinematics of the particle. Now, before ending this lecture, I would like to emphasize on a very important point. What happens for more than one dimension? Okay. Then here you see, here basically in one dimension you had two variables x and x dot, and you had one equation. Okay. And then I will use the information of the conservation of total mechanical energy, then basically you actually constraint between x dot and x, and that is why there is one constraint and two variables. So, finally, the effective variable becomes 1, and actually you can solve for the other one. Two variables are x and x dot, of course. Okay. Now, in 2D for example, if you just go to a little bit higher dimension, let us say just 2. Okay. So, there you have the unknown quantities or variables like x, x dot, y and y dot. And finally, if you think that if we know that there is the total mechanical energy is again conserved, just let us say for the case of simple harmonic oscillator. So, we actually know that half of m x dot square plus y dot square plus half of k x square plus y square is equal to constant. So, I have one constraint connecting all these 4 variables, but I have actually two differential equations of second order. One is m x double dot will be equal to minus k x, another will be m y double dot equal to minus k y. Okay. So, I actually have this, and I actually have, but if you want to write as like in terms of just first order ordinary differential equations, you will actually have 4. Okay. 2 for each dimension, and how many constants we have? Only 1. So, this is not sufficient to just solve the whole system in more than one dimension. For more than one dimension, you actually need more conserved quantities or more integrals of motion that will give you further constraints between among those variables. Okay. So, just you comment me in the forum discussions, okay, how many conserved quantities do you need in 2D and 3D in order to completely solve a mechanical problem, just an equations of dynamics. Okay. With that, I just wrap up this lecture. Thank you.